Hi, I'm Yan Yang from the Australian National University. Today I will talk about event camera data pre-training. The work is done with Li Yuanpan and Liu Liu. In this work, we study the problem of event camera data pre-training. Our model is pre-trained in a self-supervised manner. By pre-training on a large amount of unallocated event data, one can simply transfer our pre-trained model for diverse downstream tasks to facilitate the model performance. For example, semantic segmentation, object recognition, and flow estimation. An event camera asynchronously captures the time, location, and the polarity of pixel-wise changes in brightness as a sequence of events, compared with conventional RGB cameras, which record all pixel intensities at a fixed frame rate. Event cameras enjoy a high dynamic range and temporal resolution, and are robust to lighting changes and motion blur. However, the captured events of scene are spatial sparse. There are three key challenges when compared with natural RGB image pre-training. The event data only records scene changes and is spatially sparse. And for network training, it remains unclear on how to perform data augmentations for event data pre-training. Again, because of the spatial sparsity, we find that simply performing matrix learning in the event embedding space leads to model collapse, producing over-similar embeddings. Our framework is based on contrastive learning and aims to learn an embedding space that similar image pairs stay close to each other while dissimilar ones are far apart. Specifically, by using info-NCE rules, images generated from the same instance are matching pairs and their network embeddings are put together. Images from different instances are long-matching pairs and should be pushed away from each other in the embedding space. In data augmentation for event camera data pre-training, one may directly and wrongly perform these augmentations on event images. In contrast, we study how to perform event data augmentations before converting to an event image. Here, we show the comparison between augmentations after and before the conversion. When masking the event patches, one should perform masking conditional to the event patch density, avoiding amplifying the spatial sparsity of event data. To avoid model collapse during training, our key idea is to use the paired RGB image of event data as a regularizer. We have three key optimization objectives. First, instance discrimination between event data. Interestingly, embedding of the paired natural RGB image is a basis vector and provides good regularization. We project the event embedding on the image embedding before optimizing the info-NCE rules. Secondly, we perform instance discriminations between paired event and RGB images to maximize the similarity between matching pairs. Third, to better align event and RGB embedding spaces, we first separately fit two probability distributions in the event and RGB embedding space by calculating their pairwise similarity and then use KL divergences to minimize the distribution mismatches. The overall framework is shown here. We evaluate our method and state-of-the-art methods on three downstream tasks: object recognition, optical flow estimation, and semantic segmentation. Here is the optical flow estimation examples of our methods on the MVSEC dataset. Here is semantic segmentation prediction examples of our methods on the DSEC dataset. We visualize attention maps of our pre-trained model, showing that our pre-trained model successfully focused on semantic meaningful objects on the noisy event images. Thank you for your listening and time. If you are interested in our work, please scan the QR code for more information.